Good afternoon, everyone, and thanks for coming. So today our speaker is Joe Guinness. He is currently an assistant professor at NCSK, Department of Statistics, NCSK, but he is currently visiting Cornell University, so he is here for 2 days. He's going to talk about a general framework for Vikia approximations for Gaussian process. This is a very recent paper. He has put it up in the archive. It's a very nice paper, so I want to learn more about this. I have seen this paper.
You only.
All right, thanks, Soutir, and thanks to the organizers for the invitation. I have to say, I was very excited when I got an invitation to come to Colorado School of Mines because the last couple of years, I've been sort of fascinated with this particular Gaussian process approximation as due to a guy named Aldo Vecchia. And I was going to flash the paper up here, but I couldn't get on the internet. But he did his work here at Mines in the late 80s. And I don't know...
Which department?
Sorry?
Which department?
Mathematics.
Yes. Like 88, he was 88. Who was it in? None of us are in 88.
Was anyone here in the late 80s?
Did he do his PhD here?
No, I don't think so.
Is this undergraduate program?
But I don't think he in the faculty.
Faculty, yes.
Oh, he's a faculty here?
Yeah. Mathematics genealogy, he has a grad student from here.
Really?
Yeah.
Ghost
That is
professor.
before him. They didn't know.
Yeah, I didn't know.
Yeah, if you Google him on the genealogy project. Anyway, so I'm excited. Okay, so this is work that I did with a guy named Matthias Katzkus, who's at Pennsylvania. Okay, so background material. Gaussian process is a model that we use for spatial temporal data. What I mean, so spatial data can mean lots of different things. What I mean when I say spatial temporal data is that you have the data are this thing Z, and it's a real number, and it's indexed by a spatial location or a space-time pair, because a point in space and time. And then we can think of this as a function of that location, and so we think of it as a process. And then we say it's a Gaussian a stochastic process. We say it's a Gaussian process is if you take any finite collection of locations, S1 up to Sn, and then form the vector that's the response at those locations, it's a Gaussian process if that vector is always multivariate normal. Okay, very simple. So this is the model for random functions, and that it's the particular model that always gives you multivariate normal when you look at finite dimensional distributions. Okay. Now, multivariate normal is completely parameterized by its mean vector and its covariance matrix. And so for the process, we have to specify a mean function of location and a covariance function of pairs of locations. Because covariance is a relationship between pairs of variables. So that's mu and that's k theta. We'll be talking about estimating covariance parameters, but we'll just assume that the mean is 0 to make things simpler for the rest of the talk. And so some examples that I'll be using as covariance functions are from this class called the Matern covariance. So theta is a parameter, S and T are the two locations, and this is the functional form. So here there's 3 parameters, sigma squared that controls the variance of this random process. Alpha controls how strongly things are correlated, how quickly the correlation decays as you move away in distance between pairs of location. And then nu is they call the smoothness parameter. This tells us how smooth the realizations of the random field are from this model. Larger nu means more smoothness in terms of derivatives of the function. So there's lots of applications where people use these things, time series, spatial temporal data. They're also used a lot in surrogate modeling for expensive computer models. So you evaluate the expensive numerical model at a few locations and use a Gaussian process to interpolate it. We call that a surrogate. Okay. So here's just one example of the sort of data you might want to analyze using these Gaussian process models. So these are wind speed values from a satellite called JC3. And so the satellite is obviously orbiting the Earth. And so you get this like mishmash of coverage at different spatial and temporal times. So something you might want to do is you pick a time in the middle of the time domain when you took these data and try to estimate what the wind field was on all locations in the oceans. And then you could do that at different times. So, so this is using a Gaussian process model to get this. This is an estimate of the wind field at a time in the middle of that time domain, and this is an estimate of the wind field at the end of the time domain. All right, so we're thinking of the locations here are space-time locations.
So you've got space and time where you don't have any labels on your axes and so what's what?
Oh, this is the map is just space
Okay.
at a single time.
And that's what the previous graph also indicated?
This is all the data as a function of space for all the time. So I've sort of collapsed everything. So yeah, so this is space-time data that I just plotted as a function of space. Good question. Okay, so, and then these models give you sort of realistic things. So, for example, if you want to do an interpolation, so if you want to estimate the wind field at a time in the middle of the domain, then you're going to get smaller standard deviations, standard errors in those predictions. At the end, you get bigger standard deviations because it's harder to do it. It's easier to do an interpolation than extrapolation, essentially. And then you can sort of see in where the path of the satellite. So blue means a small standard deviation. So that means the satellite was here at a time very close to the time that you were trying to predict that it was today. So these are the sorts, just to give you a sense of the sorts of things that these models are capable of doing. Another thing they're capable of doing is taking a draw from the probability distribution. That's the conditional distribution of the field given the data that you've observed. So we don't get to observe a complete field, but we can use this probability distribution that's in the Gaussian process model to simulate what the field might have looked like given the data that you've observed. So this is a nice way to characterize uncertainties in predictions. Okay, so the reason this is hard is due to computational issues. So some notation here, sigma is the covariance matrix. So you take the Gaussian process evaluated at a finite number of locations, and you look at the covariance between, you use the covariance function to fill in this matrix as the covariance for all pairs of locations in the data set. And then you can write down the joint density for that random vector in terms of the covariance matrix. It has this form. Now, I'm told I'm supposed to explain what maximum likelihood is. So the likelihood function is the joint density evaluated at the data. So the data we observed is this little z vector. And we think of, so this is just the joint density for a particular value of the parameter valued at the data that we observed. And we think of this now as a function of the parameter, and we want to pick the parameter that makes the data most likely. So we want to maximize the joint density as a function of the parameter. So I don't want to go more into that, but that's what it is. And then theta hat is the maximum. Okay. So people began using these likelihood-based methods roughly in the 1980s. There's a paper where they proved that you can you get the sort of statistical properties that you hope to get if you do maximum likelihood estimation using spatial models. Okay, the computational problem. This matrix sigma theta is an n by n matrix. So when n is on the order of tens of thousands, you can no longer store this in memory. And you think about what you have to evaluate to get this likelihood function. The hard part is this log determinant term. To get that, you have to factor the matrix, unless there's some specialized thing you can exploit. And so that's an order n cubed floating point operation thing you have to do. Okay, so this becomes a problem when n is large. That's the main point. Okay, so then there's been a ton of work in statistics and also in computer science about how to deal with this problem. So I've just listed a bunch of them here. So mostly in the last 10 years, people haven't really, a lot of energy has been put into working on dealing with this problem. Okay, so I want to give you sort of a different formulation of the exact likelihood first. So this is our data vector z. So it's evaluated at all these locations where we collected the data. I define this set h of I. So I is going to be an index from 1 up to n. So h of I are the numbers 1 up to I minus 1. And z indexed by that set is just the vector composed of those indices. Does that make sense? Okay, so z of h of I is z1 up to zi minus 1. Okay, so this is, we call this the history. Even though there may not be any ordering of the observations, you still have to, when you put them in a vector, you have to give an ordering. And so this is the history in whatever ordering you picked. Okay. Now, for any probability distribution, you can write the joint density. So this is the thing. This is the likelihood function. If you think of it as a function of theta. For any probability distribution, you can write a joint density as a product of conditional density. So this is a n-dimensional version of the probability of A and B is the probability of A times the probability of B given A. So you can always do this, and this is an equality here. And the way it works is you do the condition distribution of the ith one given its history. So that's just an equality there. Now this doesn't help with computation at all. So what Vecchia said is that for each I, instead of conditioning on the entire history here, I'm going to pick a subset of the history and make that subset small. So not grow with I, as the actual history does. And then replace zhi with zgi. And what ends up happening here is that these conditional distributions are all univariate normals. And you can figure out what that univariate normal distribution is by factoring a matrix that's m plus 1 by m plus 1. Okay, so you can work with small matrices. So we're thinking of m on the order of like 10, 20, 30, 40 instead of tens of thousands. So you can approximate this density by replacing it with this one. And this one you only ever have to work with small matrices. And but you have to do it n times. So the memory burden is m squared times n. You have m squared. The matrices are side m squared, you have to do it n times. And then each of them you have to factor, so that's over m cubed. And then, but it's linear at n, so this is faster. Okay. Now it's not obvious that this will work well, but this is something you can do. So in a picture, what does this look like? So the exact joint density we break up into this product. So this is what I'm showing you pictures of are what the components of this product, what they're composed of. So here I picked okay, so let me back up a second. All the dots here are spatial locations, so these are the SIs. So we're thinking of there's a random variable associated with each spatial location, Z of SI. What I've plotted here are in black, these are the first 40 observations on this side. In whatever ordering we picked, I just picked a random ordering of the locations here. And this is the 40th one. So in the exact likelihood, when I equals 40, what you have to evaluate is the conditional density of the observation at this point, given the black ones, ignoring the gray ones. And then later on in the orderings, this is the 140th, and these are the 1 through 139 in black. The thing you have to evaluate is conditional density of this one given the black ones. Okay? Following me so far? What Vecchia said is, instead of conditioning on all the black ones, just condition on some of them and write down the density for this one given the ones that are squared. and likewise here, write down the density for this one given the ones that are square. The reason that this works well is that for spatial problems, you think, for reasonable models, now it doesn't have to be true for every model, but if you think of a reasonable spatial model, that what's going on nearby this location will contain most of the information about this conditional distribution. Okay, so you can think that these black ones are probably close to conditionally independent of this one given these ones. Meaning that if you condition on these, you get some information about this. And if you had additionally conditioned on that one, it doesn't give you much more information. All right, so think of these, if these are weather stations measuring temperature. If you know the temperature at all of these locations, you can guess what the temperature is here. And then knowing what it is here won't improve that guess much. Does that make sense?
Just a quick question. So GI will depend upon I, because you will choose effectively the locations that are closest to this location from which you want to derive information. But the order is fixed for all I. So you're
Yes.
choosing the same number for each.
I'll get to that in a second. Yes. Okay, good question. Okay.
Thank you. I have one quick question. So this approximation would work really well if the range parameter is small, if the correlation decays really fast, right?
Well,
If-
it can work well even when
If it has, say, some sort of long range dependence, will that still work?
well, what you need is short range conditional dependence. So if the correlation does decay to zero, then the dependence on this one given these will be zero. But it doesn't need to decay to zero in order for the conditional dependence of this and this to be zero given these. Okay. So, I mean, think of, yeah, markup processes give you exactly that. So markup process, you can have long, reasonably long dependence, but the conditional dependencies are zero.
So is this equivalent to approximate your Gaussian process with a markup?
It's similar, yes. Yeah. Well, depends on what you call a markup process, because I'm not conditioning on just the previous one, but a subset of the previous one.
Can I ask you a question too? Is everyone else asks a question? Isn't there a way to update? I mean, if you know the conditional distribution of Z100 given 1 through 99, wouldn't there be a rather simple update to the covariance matrix to get you the conditional distribution of 101 given 1 through 100?
Yes. Yeah, but it can be slow. So I think it still ends up being order M cubed
Oh,
if you're
okay.
doing this sequentially. And there's a paper about this in a different context where somebody's doing
So it's
this.
still slow to do it that way?
Yeah,
Okay.
the fastest thing is I'm just going to use the closest ones and
Okay. All right.
and just go for it. But yeah, there is scope for doing more research on how to actually pick these things instead of just picking the nearest
Right.
ones. But yeah. Okay, so yeah, there's been some work on this approximation. The main paper is this one from 2004. They thought about how to pick those conditional sets. One thing they thought about is that if one of the parameters in your model tells you about long-range dependence, then you don't always want to condition on the nearest ones because you'll never get information about it. So sometimes you want to condition on further away ones. Okay. Okay, so there's been some work on this. One of the things, this isn't the main focus of the talk today, but one of the things I worked on is exactly this ordering problem. So, permutation cow, mapping from these integers to these ones. Then this is the notation here for the permuted vector. If you look at these two things, so you look at this approximation to the density and this approximation to the density, they're not the same thing. So if you reorder the points and still put condition on the same things, you get different answers. Unless these things are the full history, then you do get exactness here. But in general, if G of I is always a subset of H of I, then they're not equal. So I take this as an opportunity for improving the approximation. So think about how to get good orderings that give you better approximations. And so it's hard to prove anything about orderings. I mean, applied math people doing numerical analysis are familiar with this problem. If you want to factor a sparse matrix, then very helpful to reorder the rows and columns using, but the reorderings people use are pretty much entirely heuristic, and there's some theory about them, but the theory is very loose compared to the quality of the reorderings. So I came up with some heuristic order. This is just a random one. This is where you pick them so that you get sort of a space covering set at the beginning. This is just you start the middle and move out. And this is actually the one that people have been using in practice. So you take the points and you order them by one of the axes. And so there's a heuristic that says this should work well, because if you're conditioning on all of these, then these ones should be like screened out of the conditional relationships. It turns out these are essentially the worst you can do in most situations. And these things, well, a random one works much better in some cases, and that was completely shocking to me. So I set out to sort of figure out some other things that might work well. So
before talking about convergence with respect to ordering, so there's a convergence. Certainly, you should expect convergence as m goes to m.
Yeah.
As a convergence.
Yeah.
Has anybody studied the rate of convergence and things like that? No proof, nothing. It's a heuristic.
Yeah.
Okay, makes sense. So that means expecting convergence of this is difficult.
Yeah. The only thing I've seen is that, well, it does converge to the true thing, because
Quote unquote.
I mean, it has to, because it does converge to the exact likelihood.
Doesn't you say anything about how good the approximation is?
There's not much. There's almost no theory.
There's nothing. That's right.
Yeah.
Yeah, very something.
Now,
So this is not.
I would love to see some theory. So if you have some ideas, I'd love to talk about it. And why?
Well, sometimes in stochastic approximation, instead of choosing a particular set, you do a random selection. You try to imitate an averaging with a random selection. So you could make a mixture by random. You randomly select a collection and then take a random mixture.
That might be true. My intuition has been broken so many times. I'm serious. So yeah, try.
This is quite interesting, because when you talk about approximation, it's quite different in statistics opposed to everything else. Everything else you've got to prove it works. Statistics doesn't matter. Yeah.
You're speaking to the choir. I think this is fascinating stuff. I'm actually having trouble getting this paper published, but I think it's just fascinating. Well, one of the reasons why it's interesting to me is that the improvements are really big. So what I'm plotting here is Kullback-Leibler divergence between the approximate model and true model. This, if you don't know what that is, don't worry. It's just a measure of how good the approximation is, and you want it to be small. And so this is log 10 scale, and the focus on the black dots here. So these are Kullback-Leibler divergences for different orderings. So the square is that sorting them by the coordinate, that one that was all the way on the right. The random one is here. So you get a factor of 5 improvement by just replacing this thing by a random order. And then this other one, I think factor of 4. This other one where you did the space covering set, you got additional factor of 5 improvement on that. So you get a factor of 20 improvement just by picking a good ordering at no computational cost. So the other axis is the time required to evaluate that approximate likelihood, and they're all about the same, which they should be, because we're not doing any more computation.
Wouldn't it make more sense to compare the estimates of the parameters based on the approximation and the true thing?
Yeah, there's other things you can study. One thing is there is some theory about the approximate likelihood, in that it gives you what are called unbiased estimating equations, which is a nice thing because you can calculate asymptotic relative efficiencies, which is a measure of how variable your estimate is compared to how variable it would be if you use the exact likelihood. So there's some things, and we've done those calculations. Okay, the other striking thing about this is that these are some of the other approximations that have been used, and this Vecchia approximation, it just blows them out of the water. It's just way better. So this is for this model. This is just a simulation for the model we were studying. This is the exponential covariance. This is another one of these Matern things with smoothness 1. There's a really nice paper due to Finn Lindgren and a group in Europe. They have these SPDE approximations of the Matern kernel. And these things are valid when the smoothness is an integer, when you have two spatial dimensions.
What's the range parameter?
I don't know. This is a realization. That's the. So it's a factor of 100 better. It blows it out of the water on this metric, for example. And it doesn't really take much more time. And we have code now that's faster. And so this is actually like a quarter of a second. Okay, so sort of to motivate why I'm interested in it, it's just a really good approximation. And there's it's sort of not well understood, but I have no idea why these orderings work better. There's some heuristics you can come up with, but anyway. All right, so I just wanted to tell you about that because I'm excited about it and thought you might be interested.
Where was the paper published?
It's not published.
No, the 88 paper.
Oh, JRSSP.
Oh, really?
Yeah. I'll if I get a chance at the end, I'll pull it up. Okay, so all right, so the main point of this talk, now that I'm a half hour in, is more recent work I've done with Matthias Katzfuß. So it's often the case in spatial statistics that you model the response as a continuous Gaussian process, continuous as a function of space, plus an error term that's uncorrelated as a function of space. So we call this a nugget term. Spatial statistics came out of mining engineering. And so they have one of the terms they use is nugget to sort of, I actually don't know where this comes from. I guess you get big, if you do a mine and a gold mine, for example, and you hit a nugget, the value is going to be like way bigger than everywhere else. And so there's small scale variation. I don't know, is that the heuristic people use?
No, I think that's an actual story. That you can have in one location, you have some nuggets of other material there. That's why it's a nugget.
Okay. All right, so the assumption is y is a Gaussian process, and this thing that you're adding to y is independent as a function of space. So the notation I'm going to use here is that the vector y, this is the latent thing that you don't get to observe, and then z is the observations. I want to write this up here because I'll be flashing these up and when you forget what's what. And then this thing x, I'm taking all these things and I'm putting in one big vector. So it's a vector composed of both observed and latent variables. Okay. Now, one sort of generalization is that instead of using single random variables, we're going to collect them into vectors. So L is less than N because Y1 is a vector of single random variables. And so we think Zi is the observation that's associated with the latent Yi. Okay, and the particular ordering that we pick is important. So we do Y, then Z, then Y, then Z, and so on and so forth. Okay. Now, you can do a Vecchia approximation for the joint density of this vector x. So the same thing here, we have x and then xi given xgi, where gi is a subset of hi. And this goes from 1 up to 2 times L. Now, just taking this and I'm separating it to the y part and the z part because zi always follows directly up to yi. So this condition on g2i minus 1 and this condition on g2i. And if you think about this, this vector zi, it's the observation associated with the latent yi. So if you're going to condition on anything from the past, the only thing that matters is the yi because of how this model is formulated. In fact, the zi is conditionally independent of everything else given yi. So the only thing you need to condition on is yi. So that will simplify the formula. But the y's you can condition on any subset of the previous y's or the previous z's. Okay, that's the idea. So I've separated this into y of a history set for the y's, q1i, and the z's that you condition on are indexed by q2. So q1 holds the latent conditioning set. as the observed. Okay. Now, we actually don't get to observe the y's, and we still want to evaluate the density for z. So the likely approximation is you integrate over y to get an approximation for z. All right, so why do we care about this? Why is this something we want to generalize to? So some of these popular models for the latent thing y have nice conditional dependence relationships. So for example, if we model y with an exponential covariance, then the conditional distribution of yi given its past only depends on yi minus 1. So it has this exact screening built into it. And so this figure is to say something about, in this Matern model, that you get sort of exact screening when you condition on y's. And so the Kolbat-Lively divergence actually goes to 0 in these cases, as long as you condition on enough things. So this is I'm going to go through this kind of quickly, but this is sort of the motivation for why you'd want to condition on some y's instead of z's, because you can get exact or nearly exact approximations in that case.
How big was your set in that case?
This is just a small example. So n is the number of things that you condition on. So 1 up through 7.
Oh.
So exponential, you only have to condition on one thing, the previous one, and you get exact, as long as they're ordered left to right. So that's why you get a 0 there. But you would, if you condition on a z, you don't get a 0. That's the idea. Okay. So just to summarize what you have to do here, this is what we're calling the general Vecchia approximation. The rule here is that each zi conditions on the corresponding yi. Each yi can condition on a combination of previous y's and previous z's. And the combination that you pick shouldn't mix at all, because yi is conditionally independent of zj given yj. So that's just a property of the model. So you wouldn't want to condition on both, you wouldn't want yi to condition on both yj and zj. Okay, so this set tells you what the condition on this intersection is. Okay, and so what do you have to do? You have to partition the locations into L groups so that you get these L subvectors of your big vector. You have to pick which variables you're going to condition on, and then partition that into these two parts. Which ones are going to be latent and which ones you condition on observed things. So it's a very simple rules. Okay. One nice thing that comes out of this is that several of those approximations that people worked on that I flashed up on the screen and didn't go through are actually special cases of this approximation. So we're calling it generalized Vecchia approximation. So his original one better be a special case. So this shows that that's true. So the choice you make is that these are singletons. So each of these yi's is just a single random variable instead of a vector. He picked the nearest neighbors, and he didn't formulate it this way, but if you always condition on observed things, if the y is always conditioned on z's, then you can do some algebra and see that this integral is equal to this approximation, which is exactly what Vecchia wrote down in his original paper. So the first thing that comes out is that this actually is a generalization of that. But lots of other things are also special cases as well. So there's one thing called a block-independent approximation. So you just pick any arbitrary partition, and if you don't condition on anything, and of course if you split these up, those are both also empty. And you do some algebra here, and then you can see that this is just the product of the marginals for each of these zi vectors, which is the same thing as assuming that they're all independent of one another. So this is the likelihood approximation you get out from assuming that blocks of variables are independent of one another. Now, this is not a good approximation for the joint density, but actually as a surrogate for the likelihood function, it's actually quite competitive with the best available methods. There's some good reasons for that. So even though this doesn't approximate this function well, things like where the maximum of this function occurs as a function of theta is well approximated by this, something like this. So you can use it to estimate parameters well. There's one that has been popular for a while called predictive process, so this comes out as a special case as well. So if you pick the first set of locations to be some moderately large number of locations, so call that R. So R is like 200, 100, 200, something like that. And then pick the rest of them to be singletons. And then you always condition on that first vector of variables. You always condition on y1. So every y conditions on y1. Then you can do some algebra, and this works out to be exactly the predictive process that they propose in 2000. So in a picture here, the black dots would be y1. And then this approximation assumes that each of these other dots, which are future in whatever order you pick, are conditionally independent of one another, but they do depend on the black dots. Now you can see that this is not actually a great approximation of the process, because it wouldn't be a good idea to assume these two, which are right next to each other and not separated by any black dots, are conditionally independent. Okay. There's another one called full-scale approximation. So it's essentially the same thing as predictive process, but instead of singletons in the future, you get blocks of variables. So the idea here is y1 are these black dots, and then y2 up through yl are these colored ones. So these are all. So this would be like y1, y2, y3, so on and so forth. And this one assumes that, again, they all of these variables condition only on the black ones and not previous colored ones from previous colored ones. So this comes out as a special case as well. This nearest neighbor Gaussian process is also a special case. In this case, it's the same as Vecchia specification, but instead of conditioning on observed variables, you condition on latent ones, and you get this nearest neighbor Gaussian process. There are more. Katzfuss has a multi-resolution approximation. This is actually how the collaboration started. I told him, well, I asked him, is multi-resolution really a Vecchia approximation? And we sort of thought about it and say that sort of, if we think about it in a different way. So this one you can show is actually a special case as well. Okay. Another thing about these Vecchia approximations is that you can represent these conditional relationships with directed acyclic graphs. So that just means you put your variables on a plot, and you put circles around them and you draw arrows between them. And the arrows represent what you're conditioning on. Okay, so these you can represent them by a DAG. For j less than I, so there's an ordering here, you say that xj points to xi if these things does not point to xi, if those two are conditionally independent given the whole past except for the xj. And if not, you say that it points to this. In this setting, what this turns out to be in Vecchia's approximation is that xj points to xi if j is one of the members of that conditioning set. And so you can take these things and draw arrows between them. So a quiz, see if you're paying attention. Which one does this represent? Which of those special cases? This is one of the special cases that I just mentioned.
The predictive process.
So the y's always condition on z's, but not always the same z. So this is a standard Vecchia approximation. The y's never condition on each other. This one is predictive process. So all of these y's, they all condition on the same one. This is one of these multi-resolution approximation. This gives this hierarchical structure to the latent variables, and you only condition on things that are above it in the hierarchical structure. This is this one where you just condition on latent things, so the y is just conditioned on other latent variables. These have colors, and you can see that. Well, I'll explain what that means in a second. And then this is sort of a more general thing. So here the y's condition, some of them only condition on y's, and some of them condition on y's and z's. So a nice thing about this DAG representation is you can use these representations to prove sparsity results about the matrices that you're interested in. All right, so what matrices are you interested in? This thing x, this is this multivariate normal vector, the y's and the z's. The DAG is encoded in the sparsity of an upper-lower decomposition of the inverse of C, which is kind of a weird thing. So if you write that C inverse as U transpose, then there's a 0 in that matrix if xj does not point to xi. Okay, so there's sparsity encoded in the DAG, which in turn is encoded in these matrices. Okay. And then you can compute these entries. When they're not 0, you can compute them quickly using these small conditional densities. Okay. Now, how do we get this marginal density for z? Because we don't get to observe this y thing, so we need to integrate over y and the joint density for y and z. This is what we put a Vecchia approximation on. There's a trick you can use. So this is just Bayes' rule. Now, if you take this thing and flip it with this, you get this. So the marginal for z is the joint for y and z divided by the conditional for y given z. Now again, you don't get to observe y, but in this formula, this works for any value of y. So you can plug in 0, you can plug in conditional expectation of y given z, and so on and so forth. So you can get the marginal by this formula. Now this is easy to evaluate because we have a Vecchia approximation on this. The harder thing to evaluate is this conditional density. So let's think about what you'd have to do to evaluate that. So multivariate normal has lots of nice properties. In particular, the conditional distributions are also multivariate normal. So say that the covariance, the conditional covariance of y given z is W inverse. These conditional covariance matrices are sure complements. And if you think about the entries of the block representation for an inverse matrix, the blocks are inverses of sure complements. So you can get W by, let's see. Yeah, you can get W by just taking the rows of that matrix U from the previous page and just doing this upper lower product here. Now W is going to be sparse since U is sparse, but it's not as sparse as U. So that happens when you multiply two sparse matrices together, you can get something that's less sparse than U. And you have to factor this. The nice thing is you can use this DAG theory to prove things about the sparsity of V, where V is an upper-lower factorization for W. So the DAG theory allows you to say something about what the factor of this. These upper-lower things, I don't know, this is probably not a common thing. It's more common to take a positive definite matrix and write this lower upper with a Cholesky decomposition. You get this by doing a reverse row column order of the Cholesky factor of a reverse row column order of W. It checks out. So you can use regular code to get this thing. Okay, so here's the sparsity result. The entries of this matrix that you need to get that conditional density are 0 if there's no undirected path between yi and yj on this subgraph. So you take the nodes yi and yj and all the nodes with index bigger than I. So if you think about this one, this matrix V, so this is standard vector, this is going to be a diagonal matrix because if you look at the subgraph of just the y's, there's no connections at all. So you're going to get all zeros. For this latent thing, you get a non-zero if there's an arrow pointing between them. But you also get a non-zero if you can go, so between 2 and 4, for example, you can go into the future and then back, then you get a non-zero. So you can do that for 3 to 6 to 7 to 5. So you get a non-zero between 3 and 5, even though there's no arrow between 3 and 5. So it turns out that these latent things, you can get much less sparse matrices than we started with this U thing. And so this is a problem for computation. And yet, then you can prove things about different methods. So one thing you can prove is that if you pick a regular grid of points and a coordinate-wise ordering, you can prove that this NNGP that they came up with, actually the scaling is order n squared flops to get this matrix from once you have W. And the storage is order n 3/2. And then there's a general result for d dimensions as well. The main thing to take away here is if you use this purely latent version of this general vector approximation, then you can get something that approaches n squared memory and n cubed flop count as d increases, so the dimension of the domain increases. Okay, so that's sort of a problem. So one of the things we wanted to do is to figure out a way to fix this problem. So to use this general vector approximation, which we like because you can condition on latent things and that will give you better approximation. But avoid getting matrices that are too dense and give you bad scaling. So here the problem with this one is that you can go from y2 to 5 and back to 4. And here from y3 to 6 to 7 and back to 5. But you didn't have to do that. So you can replace some of these arrows with conditioning on the z's. So if you look at the matrices that you get from this general vector approximation, then this one will be sparser because you can't get from 2 to 4 by going into the future and back to 4 on this graph. So, so we call this the sparse general vector approximation. The thing that you have to ensure is that for each triplet j less than k less than I, you can't have both. You can't condition on both yj and yk. Let's see. You can only condition on both yj and yk if you condition on yj on the kth variable. Okay, that's sort of complicated, but you could show that this gives you something that's as sparse as the original matrix. And then there's a way to actually satisfy this. So one thing you do is that standard vector automatically does this. Another is this, we have this formulation here. So I won't, subject, in a matter of time, I won't go into this, but we have a method for generating index sets that satisfy this and give you sparse approximations. Okay. We do have a theoretical result that's sort of says what we want to say. So you can prove that if you look at the KL divergence for a standard vecchia and for a generalized one and a purely latent one, that the purely latent one will always give you the smallest KL divergence, and the standard one will always give you the biggest KL divergence. So it is true that there's some sort of compromise between, sometimes conditioning on latents and sometimes conditioning on observes. The caveat here is that this is a KL divergence for the joint density of y and z, which is not actually the thing we're interested in. We're just the marginal for z. So this is, they say in other fields, this is suggestive of something that we do want to say. Okay, so quickly some numerical results, and then I'll wrap up. So this one is showing. So this is we computed this matrix V. And what I'm plotting here is the number of non-zero elements for each column of V as a function of the column. And this thing down here is our sparse thing, so it does actually give you fewer than m non-zero elements, whereas if you use one of these latent things, you get much larger. And then you can actually, there are results that tell you what is the computational cost of getting V as a function of the number of non-zero elements in it. And the result is it's the sum of the square of the number of non-zero elements in each column. So you actually just compute what the scaling is. And so these latent things, they have, this is scaling and squared, and these things we retain linear scaling. Okay, so that's a computational complexity and sparsity numerical result. You can also show that the approximations are better. So the latent thing is always better, and this is showing that if you pick a good order, you can do even better. So the green is this sparse thing, and the red is the standard thing. So this is as a function of m. And if you take this plot and look more closely at one value of m, and change how big the noise is, essentially, then you can also see differences as well. The thing to take away from this plot is that standard Vecchia does worse as the amount of noise increases. So this way is increasing noise. And the latent and the SGB tend to do better as you get more noise.
Now, what are the previous one? That's important. That's very good.
What?
Like this one. Suppose if you change the variance, so what's the variance for this?
So this is, sorry, I went quickly because I'm running out of time. But this is signal to noise ratio equals 1. So this means that the variance of that epsilon term is equal to the variance of the y term.
Okay, so this is not Mattern curve.
This is Mattern, yes.
This is Mattern.
Yeah, the y is Mattern.
Okay, so do you expect that the variance is larger, the convergence becomes slower?
Variance of what?
So you have this, when you have a Mattern curve with the variance sigma squared, right? Not for the epsilon. So the variance becomes larger, then your convergence becomes slower. Did you observe that?
Oh wait, so variance of that compared to the noise?
It fixes
So
the
if you're-
variance of the noise.
Oh, okay,
Noise
increase
ratio
that.
equal.
Yeah.
Okay, so that'll give you a higher signal to noise ratio.
Yeah, and you observe
Some weird things happen. Okay, so let me show you this plot. So that's what we do in this plot. For standard Vecchia, so this is, going this way is doing what you're saying, increasing the variance.
okay.
So it gets better and then worse. This is another reason why I say my intuition gets broken all the time by this approximation.
Okay.
These other ones, yeah, it gets better and then a little worse and then better. There's no clear.
That's right. That's
Sorry.
what one would expect.
Yeah.
Because one is not large, right? Signal to noise. Practical problems, or is it?
In practical problems, you can have a signal to noise ratio of infinity. You can estimate models
That's right.
where the nugget variance is 0. And this is infinity. This is different parameterization. So this is infinity.
Okay, fine. Good.
Okay, I should stop. Yeah, there's references here.
Alright, so we have lots of questions as we go, but more questions for Joe? I have a question. In your latent setup, it's not always a full matrix, right? It's still somewhat, there's some entries that are into, it's just not very sparse, right?
Yeah. You actually can do an upper bound for the sparsity as well, and it is still sparse typically.
Can you say more about how sparse and what that depends on? Because often it's clearly much better, right? Your latent setup.
Yeah, I think it's like, so in the U thing, which is the, just doing a Vecchia approximation, the number of non-zero entries per row is n. I think the worst case scenario for V, which is after you multiply and then refactor, I think the worst case scenario is like m squared. It's the worst you can do.
So that's still pretty good, right? I mean, that's probably still something we could easily calculate, and given how much better it is in some of the situations, especially in high noise situations, that would seem pretty useful.
No, I take that back. I'm wrong about that. It's n to the 1/2.
Oh, okay, so it's still an effect of n.
Yeah. Sorry.
Yeah, so that's a flaw. Okay, thanks.
So I have a couple of questions. The first question is, so in the very beginning, you assume that the process is Gaussian. Why do you need the Gaussianity?
Oh, that's a good question. You can set, if you have a non-Gaussian process that you know how to write down distribution densities for, you can apply this to it. You could do it. Yeah. I haven't seen it.
Yeah, you need to know the parametric model, the density, the model.
Yeah, so one thing we thought about applying it to are these models for max stable processes. So the computational cost blows up a lot when you look at as a function of n, much faster than n cubed. It's like a factorial or something. So yeah, you could think about applying it to other cases as well.
And the second thing is that you have assumed that the observations are on a regular tree.
No, I've not
Oh.
assumed that. For one of the propositions, yes. That nearest neighbor thing, yes. For
Can you show me that proposition?
just for this one. It's very hard to prove anything when you're not on a grid, because it's not, you know, you can't say what conditions on what.
Basically, you are just using the depth, the directed graph results. Just think.
Here, what I'm trying to show in this picture is that, so if this is yi, then you can get a connection between any variable on this row or this row by going into the future and back, because you always condition on the one that's next to it. So between this one and this, you take that path. So you can make these paths for any of these. So that's how the proof works for that. And they're n to the 1/2 of these. And that's why you get more scaling in higher dimensions.